Welcome everyone to session 2D, Db2 for zOS, or Db2 for zOS, sorry, data sharing, configurations, and common issues. I'm Mark Rader with the IBM Z Washington Systems Center. I've got a lot of material, but I've actually added even more material in the PDF. So when you're able to download the PDF from the GSE conference site, you'll see some additional material, mostly diagrams, to help you understand what I've got here today. Now that I've seen you and said hello, I'm going to stop my video so as to save on the bandwidth and make sure we don't get any interruptions here. Of course, I haven't figured out how to stop it. Stop video. Okay.
And just an admin notice, if you've got any questions, please type them into the meeting chat. And then at various points during Mark's presentation, we'll stop and answer the questions. And if you also can turn your cameras off, that would be great and save on the bandwidth. So over to you, Mark. Thank you very much.
Thank you, Marcus. Okay, let's see what we're going to talk about today. So the agenda is a brief overview of Db2 data sharing, and then I'll spend a little time talking about general data sharing configurations. I'll just cover some general options, but there are many variations that I've experienced with various different installations. After we go over the configurations, we'll talk about common issues in the area of performance, availability, and dynamic workload balancing. And then, assuming I get through this all in a timely fashion, I'll have a brief touch on the recent enhancements in Db2 and Db2 in the area of data sharing. So what is data sharing? Well, Db2 data sharing and parallel sysplex constitute the infrastructure, the basics that you need to provide your enterprise applications that use relational data with the highest levels of availability, non-disruptive scalability, and dynamic workload balancing. So the idea is to protect you and your applications from planned and unplanned outages, to allow you to grow, to handle business changes or market changes or even regulatory changes. And dynamic workload balancing, I wonder if there's timing here. Dynamic workload balancing lets you move workload around to available capacity, especially in the case of workload spikes. One of the reasons data sharing is popular with our customers is that your application investment is protected. So the SQL interface hasn't changed. The environment scales very well, and applications do not need to become cluster aware. So as you add more DB2s or more LPARs or both into your data sharing environment, the applications don't have to change. In fact, when they go from non-data sharing to data sharing, they don't even know that they're in a data sharing environment. So what is a parallel sysplex? I've used a simplified version here in the diagram, and we'll use that to talk about the different components that Db2 relies upon. So first, we'll talk about the sysplex timer protocol, or STP. This allows the two LPARs to agree on what time it is. This is important so that if Db2A writes a log record with a timestamp, Db2B, which may be where you run the recovery utility, can read that log record and sequence that information correctly for the recover to succeed. We have coupling facility LPARs. These are the triangles or prisms that you see on some diagrams that constitute high-speed shared memory. They're controlled by something called coupling facility control code, or CFCC, which you can think of as a mini operating system. Within the coupling facilities, there are three kinds of structures: lock structures, list structures, and cache structures, and that's where the various data, the information we're trying to share between our two Db2s is going to be stored. Of course, IMS, vSAM, RACF, lots of other people use these structures. They use their own structures, and that's how we're going to share data with high speed. The coupling facility links are how the LPARs talk to the coupling facilities, and that's important. Sometimes in the early days of data sharing, that was a bottleneck, not so much anymore. And all of these things are defined in a coupling facility resource management policy. And that's a mouthful, so I'll just say CFRM. Now, there are a couple zOS components that are important to know about. One is cross-system extended services, or XES. Some people pronounce that as an acronym. I do not, because if I get dyslexic, it distracts everyone from the topic at hand. Cross-system extended services is how the actual requests from DB2 and IRLM get to the coupling facility and how the results get sent back. So I'm going to say that DB2 talks to the group buffer pools and that the IRLM talks to the lock structure and that DB2 master talks to the SCA, but that is not strictly accurate, right? DB2 master is going to use an API into XES, and XES will then go and send the information to the SCA and bring the information back. Cross-system coupling facility is a way for the different components to communicate with each other. So the two different IRLMs can communicate with each other through cross-system coupling facility. And that's how we humans interact with the coupling facility to find out what's there. So there are display XCF commands, there are set XCF commands to see what's going on and to make decisions based on what's going on. Now, DB2 has the concept of a data sharing group. The data sharing group consists of 1 to 32 members. So what we think of normally as a DB2 subsystem, we're going to call a member when it's part of a data sharing group. Within each member, there's a single DB2 catalog and directory. So really, a data sharing environment is just a really large DB2 that's inhabiting lots of LPARs. The user data and the DB2 data is on shared disk so that all the LPARs and the DB2s there can get at it. We typically have a single location for distributed access. So whether you're saying connect to location name or doing a select from location dot auth dot table name with a 3-part name, one location will identify the entire data sharing group, and it won't matter which DB2 you end up running your query on. Each DB2 member has read-write access to its own active log, archive log, and bootstrap. Sorry, read-write access, and then it has redax to others. So DB2A can read and write to the DB2A recovery log, and DB2B can read and write to the DB2B recovery log, and they'll read each other's. Now for DB2, the coupling facilities contain 1 lock structure per data sharing group, 1 shared communications area per data sharing group, and multiple group buffer pools. The group buffer pools, there will be 1 for every local buffer pool that has data that's being shared between the members. So as a start, DB2 itself will allocate group buffer pool 0, group buffer pool 8K0, 16K0, and 32K, because the catalog and directory are going to use those. Their asterisks here indicate that the lock structure and the SCA are required structures. And what I mean by that is DB2 will not start if it cannot allocate them, and DB2 will fail if it loses access and cannot rebuild them. When we get to the availability discussion, this will become quite important. The group buffer pools aren't strictly required. If you lose access to the group buffer pools, DB2s don't fail. They're probably not going to do anything very interesting, but they won't fail. The shared communication area is a list structure. It's accessed by the master address space. Again, it's a required structure, and if we want to rebuild it, all the DB2 members have to be active to rebuild the structure. The SCA contains group-wide status information. It's generally not a performance concern, and the only real concern is if you make it too small, it's an availability concern. This has not been a problem since, I would say, the mid-90s. It looks like I can admit people who enter the waiting room. Is that true? The lock structure is accessed by the IRLM. Again, it's a required structure, and all the IRLMs that were active to build the lock structure have to be there to rebuild it in case we lose the lock structure. The size of the lock structure can influence performance. So if the structure is too small, that can have a negative impact on your applications in your system. The lock structure is made up of 2 parts, 2 primary parts. There's also some control information that I don't talk about. But from a point of view of how DB2 thinks about the lock structure, there's the lock table, which has lock table entries or LTEs, and these represent hash classes. And DB2 can get either shared or exclusive access to one entry. So what happens is anything in DB2 that we need to lock, we're going to run through a hash algorithm, and the result that comes out is the class that we're going to attempt to lock. And those are small, either 2, 4, or 8 byte entries, depending on how many members in your data sharing group. And again, the only thing XES knows is shared or exclusive, which is a lot smaller than the amount of the number of lock states that IRLM understands. The other part of the lock structure is a modify lock list. So these are record list entries or record list entries, and I'll call them RLEs. So this is more detailed information about a resource that's being locked, if it's going to be changed. So if we take an X-type lock, so think of insert, update, delete, merge, truncate, think of opening, closing data sets, think of binding packages, things where you're making changes to resources. The resources, when they're locked, will be protected by by record list entries, and those record list entries will become retained locks if DB2 or IRLM or zOS fails. The idea is, if I'm in the middle of updating my salary record and my DB2 fails, I don't want some friendly tax administrator to increase my tax withholding until I actually get my salary increase. So we're going to lock that record until the DB2 that was updating it is able to figure out what happened. So in other words, we have to restart the DB2 to release retained locks. That'll be important as we talk about availability. In the lock structure, IRLM is going to track logical locks and physical locks. Logical locks track concurrency. The idea is we're going to allow many readers or one writer to a resource. This isn't any different from DB2 version 1 release 1. We just call them logical locks to distinguish them from what's new with data sharing. Physical locks. The purpose of physical locks is to track coherency. That's the word we use to say that a particular resource may be held in more than one member of the group, and one member wants to update that resource. If it wants to change the state of the resource, the other members have to find out, because once the change happens, they now have old information. So coherency is how we talk about that. And P locks, which we use to track coherency, are negotiable. That means if I have a collision between an S request and an X request, I can negotiate through that and come up with an intermediate state. And one example of doing that is how we decide to go into group buffer pool dependency for an object. So, and we can negotiate a variety of times, right? If there's one member that's holding a lock and a second member joins, we do one set of negotiation, and then we do another set of negotiation where the third member joins. It appears that I've got automatic timing going on, so I'm already on the slide for group buffer pools. These are cache structures. They are accessed by DBM1, right, buffer manager. And these are about managing buffer coherency. So what we just talked about on the previous slide, as soon as I change a buffer, right, the page that was in that buffer may also be in Marcus's local buffer pool. And if that's the case, he needs to know that I made the change. As with the lock structure, the size of the group buffer pool can affect its performance. So if it's too small, you can have bad impacts on your performance, on your applications in your system. So I've got a little picture of some group buffer pools here. There's going to be quite a number of them potentially. They have two components. One is a directory entry. The directory entry has pointers to the pages in the local buffer pool, as well as pointers to the pages in the group buffer pool. For any particular page, let's say my favorite table space and page 13, I only need one directory entry, and I can track all of the DB2s that have page 13 in their local buffer pool, and I can track the instance of page 13 that's in the corresponding group buffer pool. The data elements are the actual changed pages. So DB2 is going to track pages whether they're updated or not, but then once they're updated, they will be written out to a data element. So these will be table pages or index pages, And by default, we're just going to store the changed pages in the data elements. There are other options. We can store all the pages, or we can not cache any pages. But typically, that's what we see is the changed pages. Once we have changed pages in the group buffer pool, we'll need to eventually get them out to disk. So that process is called cast out. And one of the DB2s will own a cast out class, and one of the DB2s will be responsible for casting out of a structure. And over time, we're going to write those pages out to disk to harden them. While the page is in the group buffer pool, it represents the most current state of the page. Marcus has a very busy DB2. As soon as he updates page 13 and it gets written out to the group buffer pool, it's going to be stolen in his logical, within his local buffer. And so therefore, it might be the only copy of the new version of the page is there in the group buffer pool. So we need to protect it to avoid lengthy recovery. And so we're going to recommend duplexing the group buffer pools. What that means is when Marcus changes page 13, he'll write it out to the primary at commit, but it'll be written out asynchronously, hopefully before commit, to the secondary structure, so that if there's any problem, that changed page has already been captured. Now, if we lose a group buffer pool, we don't have to restore all those changed pages. That can be a lengthy outage to an application. So duplexing, which we strongly recommend, I'm applying, twisted arm techniques on a customer that I've been working with that doesn't yet duplex their group buffer pools, and we'll see how effective that is. The primary group buffer pools provide all the access that group buffer pools have. So you can register a page, you cache change pages, you do cast out, and you go and look in that group buffer pool to see if a page is there if you don't have it in your local buffer. All the secondary group buffer pools do is cache the changed pages, right? So we're going to keep a copy of the changed pages on both CFs. This kind of duplexing is called user managed duplexing. It's not me as a user or Marcus or Colin, it's DB2 as a user of XES services. So I'm going to go to the divider page for the next topic and check with Marcus to see if we have any questions that need to be answered.
Well, we've got nothing so far.
Okay, well, let's roll on with configurations. So the first configuration to think about is non-data sharing, right? Before you go into data sharing, you're going to have a DB2 on an LPAR. I've chosen DB2P. I run into many DB2Ps in my experience. So I've got the address spaces that DB2P needs to support it. They all start with DB2P. I've got the local attach so that KIX or IMS or TSO and everybody else can attach to DB2 with the label DB2P. And then, of course, there's network attach. I won't talk about SNA. So for TCP/IP, we've got an IP address or domain name and a port number and a location. And in this case, I've used the location LOC DB2P. So here we are, everything's fine, and we want to go one-way data sharing. So we run through the install panels, and we decide to enable data sharing. And I recommend that you change your DB2 member name, now that it's going to be a member. In my case, I've chosen DB2A. There's quite a number of naming conventions that I've seen out there. The point is to have an elegant naming convention and yet retain the original subsystem name for your group attached name, so that JCL doesn't have to change. So in this new picture, I've got DB2A DBM1 and DB2A master and so on. And I can run the previous JCL because it's going to try to connect to DB2P, and my new DB2A has DB2P as a group attached name registered with zOS. When I get to one-way data sharing, I need to allocate the SCA and the lock structures. There's a number of reasons for this, but primarily it's so that DB2 can detect if another member shows up. So we're going to be putting some information in the SCA and some information in the locks in case someone else shows up. It isn't strictly required to define the group buffer pools at this point, because a one-way DB2 data sharing member will not allocate them. But since you have to define everything in the CFRM policy anyway, you might as well define them before you get to this point. So now we see DB2A in its interesting off-red color as the new player on the block. And we go through this again, go back through the install panels and add another member to the data sharing group. So if we follow the same naming convention, the new member will be DB2B, and it's going to live on a different zOS LPAR. And we can keep doing this up to 32 times. Once we have member DB2B, we're going to probably allocate group buffer pools. So for every local buffer pool where DB2A and B are sharing with some write intent, then we'll have to allocate a group buffer pool. And the objects that get allocated into group buffer pools are called group buffer pool dependent. Now we've added the DB2B recovery log, of course, and DB2A will have read access to it. So what are some configurations now that we're in two-way data sharing? So the original configuration, back when the operating system was OS 390, had two external coupling facilities, and therefore the lock and the SCA were isolated from the DB2s and the IRLMs. And the group buffer pools were spread across coupling facilities to balance out the load. And overall, we had 4 systems, 4 boxes, for central electronic complexes, for mainframes, whatever you want to call them. And we could tolerate the failure of any one system, or KEC, and applications would continue to access data. If we lost DB2A, we'd keep running on DB2B. If we lost CF02, we'd use the group buffer pools on CF01. And if the buffer pools weren't there yet, we just rebuild them. Okay, now we go to configuration B. Late in the 1990s, Poughkeepsie decided that it would be a nice idea if we had an integrated coupling facility. So we just repurpose an engine on one of our mainframes and characterize it as a coupling facility. So that's the integrated coupling facility. So that's ICF02 on the right, upper right on the third system. We still have an external CF for the lock and the SCA. So the lock and the SCA are still isolated from the DB2s and IRLMs. So I can lose any one of the systems and maintain application access. Again, my group buffer pools are still spread across the 2 CFs, but around the same time, we introduced group buffer pool duplexing. It was really painful if you lost a group buffer pool and had to recover all the changed pages. So we duplex group buffer pools, and now you can see we'll put the primary on one and the secondary on the other. So you'll notice that one instance of DBPY is on the left and the other instance is on the right. And you just balance them back and forth to make sure that you've got relatively even usage of your 2 coupling facilities. Now, I can still tolerate the failure of any one system, and applications will continue to access data. If I lose the CF with a primary, I start using the secondary group buffer pool. I just invalidate all the pages, and I have to perform a little bit of extra I/O until I repopulate directory entries. The third configuration, customer says, great, we just went from 4 footprints down to 3 footprints. Let's go one step farther and go to 2 footprints. Let's have 2 integrated coupling facilities on 2 KECs. Now, if you do this, yeah, we'll still duplex the group buffer pools and spread them across like we did. But now the lock and the SA are not isolated from the DB2s and IRLMs. They're on the same footprint, in this case, as DB2A. So there's a single point of failure. What happens if a system is lost? Well, I'm wearing some blue, so I can say it depends. What does it depend on? Well, it depends on which DB2 was lost. Let's say we lost KEC 3. If something happened, power off, ceiling collapse of the building, creative driving, if we lose KEC 3, then we only lose DB2B. DB2A can keep running. Yes, we'll have to recover retained locks, but DB2A will keep running and applications will keep doing work. However, if we lost KEC 1, we would lose the entire data sharing group because DB2B by itself is not able to rebuild the lock and the SCA. So the DB2B would also fail. So with this configuration, if you lose KEC 1, you have a full data sharing outage, no application access to data, which of course is the antithesis of what we're trying to do with parallel sysplex. So recommended in this kind of environment is to use system managed duplexing for the lock and the SCA. So we're going to have a copy of lock 1 and SCA on each of the coupling facilities. XCS is going to manage that duplexed, and that's why we call it system managed duplexing. DB2 is completely unaware. And just as a reminder, this is not how group buffer pools do it. DB2 knows what's happening with the duplexing, nobody else. But DB2 has no idea that the lock and the SA are being duplexed. Now, if either KEK fails, the other DB2 will keep running because it has the full lock and SCA available to it. Now, yes, if a DB2A fails, we'll have to restart the retained locks. But other than that, we can still keep doing work. Now, duplexing with system managed duplexing, as it came out in around 2001, I believe, that involves synchronous duplexing. And that means there's an increased cost for lock requests. The costs go up pretty significantly, and you can have performance and CPU costs. So performance for things like your applications, trans per second, batch job, elapsed time, all of those things, plus CPU costs, because the request from zOS to go to ICF01 is a synchronous request. The processor is not dispatched to do other work. And now it's waiting for lock 1 on each of the CFs to be updated. So lock 1 on the left gets updated, then lock 2 on the right gets updated, and they agree that they've been updated together, and they come back and they tell zOS, okay, we're done, and now we can continue. So all of that extra overhead happens while there is a processor not doing other useful work. It does not get dispatched like it does in case of an IO interrupt. So that performance and CPU costs can be mitigated with asynchronous coupling facility duplexing, right? This is something that came out, was supported with DB212. It's been out for a while, and a number of customers are using it quite happily. This allows you to duplex the lock structure without those horrible costs. I should note, we're still system managed duplexing for the SCA, right? Still synchronous duplexing for the SCA, but it doesn't have enough traffic and enough criticality to cause application response time problems and CF overhead, right? There are smaller messages and they happen much less frequently. So the fact that we have to duplex the SCA isn't going to be an issue. It's the lock structure that's expensive. Not quite finally, we have what I call configuration D, which is really just a special case of B. I've got 3 systems, and on one system, I'm using an integrated coupling facility that isn't related to work on that system. So I've got ICF02 over on KEK2, and it's not supporting a DB2 in zOS 3. So now that we have this set up, DB2A and DB2B are isolated from the lock in the SCA. So again, I could lose any one of these systems, and DB2A and DB2B will continue to provide application access to data. Finally, we have parallel sysplex in a box. For some shops who either don't have or aren't yet ready to have more than one system, but who still want the availability benefits of parallel sysplex and data sharing, they can build an entire parallel sysplex inside one KEK. Multiple LPARs, multiple coupling facilities, group buffer pools, lock and SCA. Now, there's just no hardware failure isolation. So if we were to lose KEK1, there's an outage, right? Everything's gone. But if you only have one system and you lose it, everything's gone anyway. We do have protection from planned outages for software changes and unplanned outages for software changes, assuming that applications are cloned and can run on either LPAR. So there is still a risk of hardware outage for unplanned outages, of course, and for some planned hardware outages. So any questions, Colin, come in about the configurations?
No, nothing yet.
Okay. So probably this is the post-lunch coma, and I've put everyone to sleep.
It's a bit quiet. I don't know why. Need to nudge them.
Right. So let's talk about common issues. The first one I want to talk about is performance. The design goal with data sharing is that if you're not actively sharing data, there'll be little to no performance impact. So we call sharing data inter-DB2 read-write interest. That's where 2 DB2s are sharing data and at least one of them has write interest, right? So now we need to worry about locks, we need to worry about group buffer pools, and be able to dynamically recognize when sharing happens. What that means is Colin doesn't say, oh, I'm going to start data sharing. He just starts running work on another LPAR. And boom, DB2 understands and starts doing data sharing. Once we get into data sharing, we want minimal and acceptable overhead for that intra-DB2 read-write interest. Now, overhead will vary based on workload characteristics and configurations. And then once we get that minimal overhead for two-way, we want pretty much linear scalability as we add 3 through 32 members, right? So however many members you want to add. Most of the overhead appears going from one-way to two-way. That's where we get the additional messaging. And then there isn't a big bump when we add the third, fourth, or fifth. There is a little bit, not a big bump. So what does this look like? Well, if you think of a simple performance graph, as I add members, I scale, but I don't scale perfectly. You can see that the arrow is shifted a little bit to the right when I added the second member. And the arrow isn't exactly at 45 degrees, right? But it's very close. Now, the critical factors in data sharing performance are concurrency control, right? Making sure we have multiple readers or one writer, but not both. And we're going to do that with global locking. And inter-system coherency control, where we're managing changes to data, where one system changes a page or resource that resides in another system. So for concurrency control, we're talking lock one. And for coherency control, it's a combination of lock one and, in the case of buffers, group buffer pools. We do not have a group EDM pool, right? We do not have a group dynamic statement cache, but the resources that might be in there could be controlled by locking to make sure that we aren't overriding. Actually, dynamic statement cache was a bad example, but binding packages would be one. Now, to manage these factors, there's messaging, right? We send messages back and forth to the lock structure and the group buffer pools, thousands to tens of thousands per second. My early extreme example, it was my personal record at the time. I worked with a customer who had 166,000 synchronous lock requests per second to the lock structure. They still had excellent performance. Since then, I've encountered in the last couple of years several sites that have over 200,000 synchronous lock requests per second, and some much higher. And then I've seen a report from a customer, a large financial institution, with over 643,000 synchronous lock requests per second. And that, by the way, that number is an average over an RMF interval. So you can imagine that the peaks within that interval are even higher. Most of these coupling facility messages for DB2 or IRLM are synchronous. And again, this means that the host processor is busy. So whether it's a general purpose or a zip that dispatched the request to the coupling facility, it isn't doing other work until the response comes back, right? So that's overhead. But we're willing to pay that overhead to get to the availability and workload balancing benefits that data sharing provides. So we just need to manage the performance costs effectively. So what is it that influences those performance costs? Well, there's hardware configuration. How many of your resources do you have? Do you have any bottlenecks? Do you have a slow CF? Lock contention rate. If everybody's always going after the same resources, you're going to get more overhead. And of course, CF access intensity. So if you have a particular workload that doesn't need the CF a lot, then it'll be cheaper. If another workload needs the CF a lot, it'll be more expensive. So if we take our same graph of performance and members, where that arrow goes depends on all these factors on the left, right? And so what you're going to try and do is manage so that the arrow is as close to 45 degrees as you can get it. Now, typical data sharing, when I'm doing planning for someone who's first going to data sharing, I'm going to suggest that the overhead going from one-way to two-way is about 10%. Now, this is relative to the overall workload, right? Imagine all of your workload is a big box. So that box is going to get 10% bigger when you split the workload across two members and two LPARs and do full-on heavy data sharing. Individual jobs or transactions will have higher overhead. The IRLM, for example, is going to go up by a lot more than 10%. But the IRLM is tiny in the grand scheme of things. So doubling or tripling the IRLM processing is not going to be a major contributor. And then after two-way, typically we're looking at 0.5% of overhead. for each member that's added. It's important to maintain a balanced configuration. A balanced configuration means the coupling facility technology is comparable to the host technology. A slow CF will make the host wait a lot longer. At least 2 CF links for each host CF combination, and at least 2 dedicated coupling facility engines per coupling facility LPAR for production. You don't want your production workload to be slowed down because one CF engine is too busy. So what are the common issues? Under-configured coupling facility is one. You might have too few engines or not enough memory, or the structures are too small, or you have some link contention. Another one is unbalanced host and coupling facility technology. I suggested this earlier. If the CFs are slower, that's going to be a problem. If you have a heavy update workload and aren't able to cast out quickly from the group buffer pool, that can slow applications down because they have to wait for their pages to get written to the group buffer pool. And finally, if you have a high rate of physical close and then physical open for a data set, that drives Db2 to go in and out of group buffer pool dependency. So we end up with lots of page set PLOC negotiation, and that can be expensive. So I've got information about all of these hidden in the handouts, but I'm going to spend a little time on the first one on the left, that is the under-configured CF. But before I do, when you look at these things, you have to decide which team in your organization is responsible for managing these resources and ensuring that you get the best performance. Is it your performance and capacity team? Is it your zOS team? Is it your Db2 team? Is it development? Are they talking to each other? Right? These are all important questions to make sure that each of the teams understand so they can communicate and you can get the best performance in your environment. So that first column was under configured CF. So too few CF engines means high CF busy. And if an engine in the CF is busy, it's going to increase the host overhead because it can't respond quickly to host requests. So the important thing here is to monitor synchronous lock request service times and conversion to async. If XCS sees really long, service times, it will convert synchronous requests to asynchronous. The good news about that is that the host processor can be dispatched to other work. The bad news is that the request takes a lot longer and the application is going to take a lot longer. And if you have a lot of it, it's going to start affecting your trans per second. If your lock structure is too small, you may have increased false contention. False contention is where 2 different DB2s are locking resources, and when they go through the hash algorithm, they end up pointing to the same lock entry. Well, that's not real contention, that's false contention, and it's resolvable, but you resolve it with overhead. There's IRLM messaging, so we want to try and keep that to a minimum. And if you don't have enough record list entries, right, if IRLM can't record the change locks in the RLEs, then it slows down. It will reserve 10% for must complete. And if you've got only 10% left, you can't ask for a new lock. And if it gets even busier, then it won't let any locking happen until something finishes. If group buffer pools are too small, and frankly, this is more frequent, you can get write failures for the changed pages, right? If I'm trying to write a whole bunch of changed pages after the group buffer pool, and the group buffer pool is too small, and I haven't been able to cast the pages out quickly enough, then these pages will have to retry and retry and retry, and eventually they might get put on the logical page list. Once they're on the logical page list, nobody can access them until we do LPL recovery. Now, there's no data integrity, but there is application performance implications. If your group buffer pool is too small, you might have cross invalidations due to directory reclaims, right? Every time I read in new pages, I have to register those pages, assuming the object is group buffer pool dependent. If I can't register them in a directory entry, then I'm going to steal one. And the pages that were being tracked by that entry are going to be marked invalid, which might drive not only overhead, but also unnecessary IOs. So the monitoring tools for you to use are things like the RMF coupling facility activity report, Db2 statistics reports, and the Db2 display group buffer pool output, because they'll tell you lots of information about these things. Questions on performance before I get into availability?
No questions yet.
Excellent.
We're shortly running out of time.
Yes. From a point of view availability, we want parallel components, no single point of failure, and take advantage of the zOS fault tolerance to be able to isolate failures and allow for automation of recovery. So we can get around any single one thing failing, but not two. And we want to be able to keep applications running without this. Now, that recovery automation means that someone's responsible for planning, testing, and updating recovery automation to make sure that as new features get rolled out, the automation does what it's supposed to do. Now, your parallel sysplex has a bunch of resources, right? You're going to connect your clients, employees, partners, suppliers, whatever, to your environment. And in your environment, you're going to ideally have a number of applications. And if they're cloned, you can route around failures. The various transaction managers, MQ, Kix, IMS, WebSphere, and so on, as well as DDF, will be resident on more than one LPAR, so they can handle those applications and route that traffic around any failure. The data sharing group, right? We've got multiple members, and we're sitting on multiple zOS LPARs. So we have parallel resources for all of this. Now, what do we do for a planned outage in this environment? So in this case, I'm going to quiesce Db2 to put on some maintenance. I'm going to put on the maintenance, and while I'm doing that, the applications are being routed around to the other members. So I can keep running, and theoretically, I can apply maintenance on Tuesday afternoon. Nobody does, but there are plenty of customers that I work with who have work coming in even in the middle of the night. So they can do this in the middle of the night and while their work is running. So you can do this for, rolling maintenance or release migration, right? We can do this thing for rolling maintenance out or for migrating to a new version of DB2. So you just point DBA to its new set of libraries while it's quiesced, then restart it, and it's coming up with the new maintenance. And then we're going to stop DB2B, right? In mode quiesce, point it to new libraries, bring it back up, and just roll through all the members. So this is good for rolling IPLs. It's good for hardware changes. We can do all of these things. What about an unplanned outage? If we lose a DB2 or an IRLM, the odds are we're going to have, yes, the applications can route around, but the odds are we're going to have some retained locks. So there is a retained resource in the RLE, it turns into a retained lock. So one or more applications will be affected by it, and they can't get that work done. So we do want to restart that DB2. It just failed in place, so we restarted in place, and assuming the restart is successful, we clear the retained locks, and we're back to where we started. We strongly encourage automation to restart DB2s in place, and most customers I work with do that. What about an LPAR outage? So if your zOS LPAR fails, that's going to affect the DB2 and probably other subsystems. I picked an MQ and a Kix region in this case. So they're all going to be out, but the other resources are still available, and we can route work around. We're going to have retained locks to consider. And as we route the other applications around, the only thing we have to worry about is what if the other applications want to get to those retained locks? So we need to restart that DB2 on another LPAR before we wait for zOS 1 to be re-IPL'd. So we're going to route this. In this case, we're going to go to zOS 2. And once that restart is complete, we clear the retained locks, and all the applications can run. Now, we still haven't finished IPLing zOS 1, and we're fine. We're back to where we can run. Now, the MQ and the Kix that still have X's on them, maybe you had to start them on zOS 2 to release retained locks. Maybe they're just going to wait, and they'll come back up with zOS. We want to restart automate the restart of DB2A. You can use Start Light if you're concerned about your memory footprint, but what you don't want to do is wait for the IPL, because this is what the IPL looks like, right? Who has the authority to say IPL zOS 1? Who has the authority to say, yes, we're executing this plan, we're going to IPL? And oh, by the way, what time is that? Is that 3:20 in the afternoon when everybody's available and all I have to do is grab a decision maker out of a meeting? Or is it 3:20 in the morning? So this should be automated. What about coupling facility outages? Those are important resources. Well, for planned outages, when the coupling facilities were first set up, we plan to have space for all the structures. So we just build the structures into those spaces, and we've moved all the structures from couplability 1 to 2, and everything's fine. No outage to the data sharing group. Now, yes, individual transactions might see slightly elongated response times if they're running while this is happening. And by the way, don't trust my syntax here. Read the manuals for the full list. For unplanned outages, we're going to basically do the same thing. We're just going to have DB2A and DB2B cooperate to rebuild the structures. Duplex group buffer pools revert to simplex. And again, there's no outage to the data sharing group. So what are some common issues? Restart processes rely on manual decisions or are not automated. So it's going to take time for someone to execute. And that just slows down because the likelihood is that those retained locks are going to be needed by multiple applications. Single points of failure. So for example, a 2KEK or 2ICF configuration that isn't using system managed duplexing. I don't care whether you use synchronous or asynchronous system managed duplexing, but in this configuration, that's what you should have. Or if your applications aren't cloned and they only live on one LPAR and you lose that LPAR. Long-running units of recovery can be a problem because when you go to back out a long-running unit of recovery, that's going to affect service restoration for potentially an extended suite of applications. Again, which team is responsible? Is this the performance team, zOS, DB2, development? Long-running units of recovery is development for sure. So what you need to invest in is automation, deploying system managed duplexing if you have a 2KEK, 2ICF configuration, sysplex enabling applications so they can route around failures, and identifying and shortening units of recovery. This is an application focus, so your development teams can work on it, and there are some subsystem parameters to capture messaging to help you identify candidates. I have a lot of hidden information in the PDF, but let's move on to workload balancing. Our common issues around workload balancing. So again, the idea is we have a single DDF location. We have a single system image for everything. And everything local is going to attach with a group attached name. We have a location alias for distributed traffic to only go to some DB2s if we want to do that for various reasons. We have subgroup attach to allow that for local attach, but primarily everything looks like a big system. Commands, utilities, binds, DDL, authorization, all of these things have group scope. If you're allowed to do something on DB2A, you're allowed to do it on DB2B. If you have external stored procedures, your WLM application environments can run in any place if you use the symbolic I've got listed here, which allows the same application environment, think JCL, to be run on any of the LPARs. And if you're replicating your log, IFCID 306 is gathered for all the members to allow log replication to work. So it looks like one great big DB2. Now, the thing about dynamic workload balancing is this is primarily about availability and application access. It's about the ability to react to workload changes and take advantage of available resources. It's not about making sure that I have exact even distribution, 33%, 33%, 33% across my 3 DB2s. So COM server provides sysplex distributor to help figure this out. MQ shared queues will allow MQ to work on multiple LPARs. KIX Plus Systems Manager, or CPSM, you can use for many things, including routing work between KIX regions and around failures. IMS Transaction Manager has shared message queues and batch message processors, again, to take advantage of the resources across the parallel sysplex environment. WebSphere, whether it's a full-blown WebSphere application server or WAS Liberty, can do the same. And of course, DB2's own distributed data facility works that way. We can take work incoming through a dynamic virtual IP address so that it runs on any DB2. Workload Manager is going to provide input to the routing choices that each of these components makes. Right, so for DB2's case, WLM is going to give DB2 a health identifier. So I've got a single example here for distributed traffic. This is a WebSphere example. In this case, I've got a distributed WebSphere, and it's got a type 4 driver going over the network to DB2. And what it has is transports, right? The driver has a transport, and that's going to connect to what we in DB2 for zOS think of as a connection. So when it first starts, the transport is going to reach out to sysplex distributor to find out which DB2 is available. Sysplex distributor is going to identify the DB2A is available, and it's going to send that information back. And so transport 1 is going to reach out and establish a connection, a DB2 connection with DB2A. Over time, we don't have to keep talking to sysplex distributor because DB2 will pass back a weighted list, a list with the systems in the data sharing group ordered by the weight, and the weight is determined based on their health with input from DB2 and WLM. So over time, the various logical connections that the applications are using will be using different transports and will connect to different members of the group. As each transaction commits or reaches a rollback, it can disconnect and use a different transport. And over time, we would expect that all the transports would have connections to all the members, and you would see an even flow of traffic everywhere. But again, it's not designed, it's designed for availability, not specifically for even balance. So some of the issues around workload balancing, the most common issue I see is that people don't enable applications or subsystems for the parallel sysplex. They put the parallel sysplex in place and then stop, which means that applications are depending on system resilience rather than taking advantage of the sysplex resources. This makes it hard to manage planned outages, and it means that workload spikes can lead to performance problems even when there's plenty of capacity available in the sysplex environment. From a DDF particular case, that means going after a single DB2 member rather than the data sharing group, or having DDF applications that are not using sysplex workload balancing so that once they connect to one member, they're stuck there. Okay, recent developments in DB2 data sharing. In version 12, we delivered a number of things after continuous delivery, as after GA by continuous delivery. And then of course, DB2 13 has just come out, so we have new things there too. So in DB2 12, we have improvements around IRLM deadlock processing to increase the speed and reduce the overhead. We've put in retry for the automatic recovery for the logical page list, and group buffer will recover pending error conditions. We've always had automatic recovery, and now we're putting in a retry so that if the first attempt at automatic recovery is successful, DB2 will retry and retry so that a DBA doesn't have to go do a start database. Asynchronous cross-invalidation of group buffer pools is useful because that means the invalidation of objects doesn't have to happen at the time that the change pages are written to the group buffer pool. And because we can, that means the applications can continue ahead and we'll wait for the cross-invalidation later. Of course, it has to complete before the commit completes. But this can be very important if you have distance between your CFs and your LPARs. And then finally, we made changes to alter group buffer pool to increase the ratio of directory entries to data elements to 1024 and to change the default ratio from 5 to 10. The last thing in version 12 was sysplex support for multi-factor authentication and IBM RAC FPass tickets. In version 13, IRLM can dynamically trigger increase of lock 1 size, producing more RLEs. So XCS has always been able to dynamically increase the lock structure and give you more RLEs, but that's designed for slow growth, not as workload spikes. And IRLM is going to trigger more quickly if it identifies a workload spike. I have a hidden slide with pictures for you. GBP residency time. We're going to see how long directory entries and data elements reside in their corresponding group buffer pools. The idea is to help you decide which group buffer pools deserve to be larger and which ones deserve to be smaller so that you can appropriately allocate your coupling facility resource. Group buffer pool cast out speed has been enhanced. So if the group buffer pool gets full, you need to cast out the change pages to allow room for more change pages. So we're going to both check more often to see if the group buffer pool is full, plus we're going to check more often to see if the full condition has been relieved so the applications can proceed. So both of those things are happening they're faster by 1 order of magnitude. And there's a particular case with universal table space partitioned by range, where we're using relative page numbers, right? These were new in version 12. And if you're doing row level locking, there's a chance that the page p-locking that happens to support row level locking and data sharing will go to a reduced portion of the lock structure and cause increased contention. So all you have to do in version 13 is do a reorg of those objects, and the p-locks will be spread out appropriately. If you convert to PBR RPN after you're at functional level 500 of DB213, you don't have to worry about the reorg. In closing, data sharing technology allows DB2 to deliver continuous availability and nearly unlimited scalability into the future. It's a proven technology. Most of the medium to large shops that I visit are using data sharing. And parallel sysplex and data sharing is considered the gold standard for enterprise applications and provides critical resources to the hybrid cloud. And of course, DB2 development keeps enhancing data sharing, so it gets better and better, even for all the good things it's been doing. Please submit your session feedback. I hope that you've been through this already today. So the session is 2D or 2 Delta. There's a QR code here. If you have questions after the fact and you want to reach out to me, you can send me an email. Depending on the week you catch me, it may take a while to get back because I've been very busy recently, but I will get back to you. And hopefully, Marcus, I think we've got a couple minutes in case any questions have come in, or if you want to open up for on-the-fly questions.
Nothing's come up yet.
Great.
Any questions? Well, I think that's it. So thank you very much, Mark. That was a really interesting session. This is session 2D for your feedback. And please, everyone, can you fill in your feedback forms, because it enables us to provide you with good content for future conferences. Okay, so we have half an hour break. And in half an hour, we have Keziah Knopp, one of Mark's colleagues, who's going to talk to us about DB2 for zOS and REST services, something that I'm personally interested in. So I'm looking forward to seeing you all soon.
Thank you, Mark. I'm going to go ahead and stop sharing, and if I can figure out how to do it, and talk to you later.